апробаторы материал. Сейчас это посмотришь на телефоне, ты увидишь, что сейчас запись. Да, я могу дать тебе адрес, ссылку дать. На нашем сайте. Где я буду смотреть, это здесь. Второй, да. Я сейчас поворачиваю. Должен пройти где-то минут 15 секунд. Посмотри, тоже здесь. Пауза. Нажимаешь один раз. И вот это остановить, стоп, это остановка. Когда заканчивается полностью комплект. Комплект, нажимаешь комплект ивент.
А как мне нажать комплект? Тут нет стрелочки вниз.
Вот это джойс. Это еще и джойс. Это еще и меню, это еще и джойс. Но ты здесь используешь не как меню, а как джойстик. То есть не нажимаешь на него, а просто идешь вниз, вверх. Да. Мы сейчас ставим на это старт, стоп, старт.
Да.
Вот только этим сейчас. И зум.
Вот, потом я включаю.
Сейчас мы пойдем. Вот сейчас так. На стоп, еще раз нажимаешь и еще раз.
Good morning, ladies and gentlemen. Initially, this lecture was planned to be delivered by head of the laboratory of steroids, Professor Vladimir Grimbach. Unfortunately, he could not attend that meeting due to institutional commitments. The main achievement of the laboratory over the years of its existence was the registration of two preparations based on personal steroids, epine and epine plus. The active ingredient of epine is epipersonalite, and those of epine plus homopersonalite. Epine and epine plus at extremely low doses, 20-50 milligrams of active ingredient per hectare. They are not human, animals, insects and fishes, and these preparations are recommended for enhancement of crop yield, increasing the oxygenation, shortening the period, formation of fertility, and so on. Of course, the registration of this preparation did not mean that works of these compounds were stopped in our laboratory. They are going on, and here I'd like to discuss some some directions which these investigations are going on in the laboratory. One of the problem of chemistry of person steroid is that the most active compound of this group, personalite, is available only for scientific research. This makes this compound because of absence of method of its preparation. So one of these directions is the development of new approach to synthesis of this compound. Such steroids are possible without labeled compound. And here I'd like to discuss fluorescence steroids. Also shows that fluorescent steroids can act not only on plant plants but also outside plant kingdom. And along with fluorescent steroids, other directions of investigation of steroids are going on in our laboratory. I will try to discuss synthesis of plant-specific steroids and synthesis of metabolites of anabolic steroids. Content of fluorescent steroids in plants are very low. The richest source of these hormones are plant pollen. But even in cases, 40 kilograms of red pollen, only 4 milligrams of personalite will be isolated. After very long purification, this is the only source of the most scientific and practical purposes is chemical synthesis. Here you can see such of the most important and most active fluorescent steroids. All these compounds containing viral centers are too complex to be prepared by total synthesis. Partial synthesis requires the appropriate starting material. On this slide, you can see sterols which can be in principle used for the preparation of fluorescent steroid without the necessity to change or to modify carbon skeleton. Aniversterol, and stimusterol are available in living plants through gist and through tubing. They can be used for the preparation of personalite and homopersonalite respectively. Unfortunately, the supply of 22-decadyl cholesterol is very limited. That is why synthesis of personalite cannot be system. Usually it is done via the aldehyde serum, which is available by analysis of this delta-22 steroids. Construction of personalite side chain is the most difficult part in synthesis of personalite due to the necessity to form 4 contiguous chiral centers. At the same time, this is the most interesting and interesting part of synthesis of steroids. Approach with the construction of personalite chain. First, the reaction of steroid to aldehyde with reagent produced reagent having a bulky skull probe. So, also published 6 years ago, the scheme is the best one at the moment. Thus, compound 12 can be obtained starting from the aldehyde 6 in 5 steps and 42% of overall yield. Another advantage of this approach is that it allows preparation of biosynthetic precursors and quality of personalite, for instance, progesterone and cricolite. The aldehyde 6 containing all the necessary functional group characteristic of steroid inside the part is a very good starting material for the preparation of personalite itself. Its synthesis has been described starting from stimusterol, but this synthesis is very long and ineffective. We propose preparation of this compound starting from aniversary 2, which is available in bulk amount, starting in bulk amount as an active ingredient of repeat. And all periods to synthesis of the personalite is oxidative cleavage of this chiral group. Naturally, such cleavage. The problem of differentiation, the two the reaction of this compound with personalite was shown to process preferential effect. This stable enough to allow protection of another that rock as a tonight, but in a mixture of triacylamiide and water, an equilibrium between 4 and 5 took place, and this compound, in the presence of sodium periodite, which was present in the next picture, gave the aldehyde 6. This compound was used with the preparation of personalite 9 using method for the transaction of the side chain which was discussed above. Study of steroids by synthesis metabolism mechanism agent is not possible and here I'd like to discuss synthesis of the letter. Tagging of biomolecules with a fluorescent level is one of the common techniques used for a wide range of applications. A lot of fluorescent level was purpose. The common disadvantage of such compounds, such conjugates, is that they are derived by a covalent budget of perform with one or more functional groups of steroids. That leads to the conjugates with properties different from the it is difficult to expect characteristics of steroids properties from conjugate to all hydroxyl group in which above as moronic esters. In this respect, the primary aim of this part of our work was to develop such conjugates in which functional groups of steroids would not be used for the attachment of First two conjugates 5 and 7 were prepared as epipersonalite or epipestosterone. The reaction scheme, synthetic scheme, included formation of a new side chain containing a C26 hydroxyl group, to which this dye was attached. The fluorescent properties of these conjugates were shown to be suitable for studies of steroids in living cells. Another conjugate was prepared using late-stage CH functionalization. Tetracetate, epipersonal tetracetate was reacted, was subject to CH amination with protein H amination with oxide sulfonamide group. The reaction proceeded with the formation of compound 3, which was isolated in 18% group along with 67% of the recovered starting material. It should be noted that only 4 steps are necessary, only 2 steps are necessary to functionalize epipersonalite. For comparison, the noun synthesis of steroids functionalized at this position have been performed in 21 steps, that is significantly longer. Other oxide sulfonamide group is reacted with those amines and we easily coupled compound 3 with amine 4 containing an azide group. Free reaction of the derivative 5 is led to the formation of the you can see this It was shown in our laboratory the treatment of lung adenocarcinoma cells resulted in creation of related toxicity species. The most transparent was observed for 22 S-26 homocysteine, which at concentration 75 caused a six-fold increase of this species. These results were obtained from the combination of non-antitumor agents with corticosteroids. Thus, the combined application of cisplatin with corticosteroid with corticosteroids proved to be more efficient than the main this toxic anti-cancer agent can be used in lower doses. Now we are entering expanded practical application of preparations based on corticosteroids outside lung kingdom. The main achievements are food identified now having adaptogenic and stress protective properties. Veterinary preparations are depressing for treatment of this and preparation critical for medical use. Vital antidepressant and medicine have been registered and developed for practical application, and the whole is entering clinical stages. Vitamin D are as compounds which are involved in the regulation of plasma homeostasis. At the same time, many other effects of this group of hormones, their practical use is limited by very strong hypercalcemic effects of vitamin D. A lot of efforts have been done to distinguish this hypercalcemic from useful effects, and the best results were obtained for steroids having, I would say, two side chains, 21 derivatives of vitamins D. We propose a new approach to the synthesis of such compounds, which is based on the reaction of Milankovitch reaction of polyphenol and 40 cyclopropanol 2. Ring opening of the cyclopropanol with diesel zinc, followed by annihilation or accumulation of the intermediate homoenarate 3, that is the formation of substituted compounds 4 and 6. The project metabolized annihilation of two toxicity to give related product 5. In the last part of my lecture, I'd like to discuss the synthesis of long-term metabolized steroids. According to Academiei, steroids are misused to extend in sports by athletes to remove their this use is followed by the analysis of metabolites of important components which has to be considered in which these compounds can be detected as examples. Typically, it is 4 to 8 days. About 10 years ago, we show that metabolites can be detected for a much longer period. Thus, metabolite and metabolite can be detected within 19 days. The use of someone for standard for similar situation is with our 3 metabolite, 4 of which can be detected within 40 days. We have developed the synthesis of this fragment and used it for the preparation of this metabolite. You should notice that this is the first synthesis of such metabolites. We competed with Austrian chemists and managed to publish this plan 1 week before. The synthesis of this compound. Until chemical synthesis, such metabolites point of view. And our synthetic scheme was based on the, in fact, the main problem which has to be solved is to change to inverse configuration of this temporary carbon atom. You can see it's hydroxymethyl and at the final compound also, but it is another configuration. And all this, nearly all the stage directed on the solution of this problem. And the reaction in this acceleration from compound 6 to 7. In conclusion, I'd like to thank members of our laboratory who have contributed to this work. You can see them on this slide. They organize the for me for creating efforts and attention.
Thank you very much once again. The next communication and checking of multiple water function and health transformation applications. Professor Institute of Inorganic Chemistry and Structural Chemistry, University.
Good morning, everybody. Thank you for coming at this early hour. And the schedule is a little bit out of order, but I like to start by thanking the organizers for inviting me to this wonderful event, the 60th birthday of the Institute of Chemistry at the Academy of Science of Moldova. And I'd like to start by wishing a lot of success for the next 6 years. So in my work, I am doing chemistry. MOFs are porous materials, and they can be called organic hybrids. And as such, they are porous materials which are placed in between inorganic porous materials, such as zeolites or silica gel, and organic porous materials, such as active carbon. The special thing about MOFs or metal organic frameworks is that they have defined identical pores and that the pore chemistry, the pore surface area, can be designed because pores are mainly constructed by the organic ligands. So MOFs also have often a higher surface area than inorganic porous materials or organic ones. So typically, you can reach pore surface areas of 2,000 to 4,000 square meters per gram with MOFs, while zeolites or active carbon are only around 1,000 square meters per gram. So 3,600 square meters would be half a soccer field, which is depicted here for the average surface area of MOFs. So how are MOFs constructed? As I said, they are called inorganic hybrid materials also, and as such, they consist of metal atoms, and organic linkers, which combine both into a porous, three-dimensional network. So the metal atoms are not single metal atoms, but combined to small clusters, typically. So here you see 3 chromium atoms combined into a triangular chromium cluster, and then the carboxylate groups from the linker bridge between the chromium atoms of this cluster and further on to the next cluster, and thereby they give this porous network, which you schematically see down here. So it is very difficult to depict these three-dimensional networks in a clear fashion, and often when a schematic network is used. Also, a single formula doesn't make much sense, and that's why often acronyms are used to describe name MOFs. So this MOF of chromium terephthalate MOF would be called MIL101 and MIL101 chromium. So in the second example, and then the last example, which I described in more detail, that also the metal atoms could be combined to a linear chain, so an infinite unit. And here the aluminum atoms in this chain are bridged by hydroxyl groups and a carboxylate group, in this case the fumarate linker. And then you get this square, almost square channels, which extend along the A-axis or the U-axis here in this network. So this is more called aluminum fumarate or alpha abbreviated, and it's also made by industry, BASF, and it's a company which made MOFs, and they then called their MOFs basolite. And this one would be called basolite. So now the second part, why do I work with MOFs? What is the application which I'm after that has to do with culture of living, society, human life? And as you are very well aware of, to live comfortably in many parts of the world, we often require cooling or heating, both. So cooling, for example, is done by conventional air conditioners, which are run on compression, and we need a lot of electricity. Electricity, for a large part, is made by fossil burning. So just to give you an idea of the amount of energy going into modern buildings, you can say that 50% of the energy consumption of the building is used for cooling or air conditioning purposes. It can be cooling or depending on the season. For example, when it comes to cooling, you can think of what nature does to cool systems like us or plants. And nature cools by evaporating water. So when water goes from the liquid to the gaseous state at 25 degrees centigrade, it needs more heat of evaporation from the environment. It's 2,400 kilograms. So six numbers has evaporative cooling. So plants cooled by have water perforated from the leaves. Now this may look a little bit old-fashioned, but a simple setup shows you here that this technology can only used for modern ways of cooling. The simple setup here, water-filled flask and absorbent flask are connected, and the valve here is initially closed. Once you open it, the infrared image shows to you that the water-filled flask will cool down to sub-zero temperature, so this is 100 degrees centigrade, and here the heat of absorption is given off in this absorbent material. So this is then called absorption chilling. So the absorbent material of high air or the air normally evaporates water and sweat, and the absorbent material then drives the water to evaporation. And thereby you get useful cold here on this side, and you could also use the heat, which is given off here on that side. So in a way, you have a heat transformation system. Of course, technically, you have to do the process in a cyclic fashion. So that means you also have to use heat again to to dissolve the water from its raw material, but this heat can come from waste heat, which you often have in industrial processes or power plants, or it can be solar thermal heat. And then altogether, such an absorption chilling process only needs 1/3 of the electrical energy of a conventional air conditioning unit. So I'll come back to this diagram. Tell you that this process can be already is on the market. So here you see commercial devices by different companies, and also here you see a list of companies which manufacture such devices on different performance scales, up to 1 kilowatt to buy such devices. So you may of course ask, why would I use it in single-family homes? Piping to and so that's why such devices are usually installed in commercial server centers or large computer facilities. These processes then I use to recycle or to cycle. So as shown previously here, the working cycle and regeneration cycle is done simultaneously in 2 different chambers, and thereby you can modulate the cooling or heat you get from such a device. So of course, you need a material, you need a chemical material to use such a technology. At the moment you have zeolites or silica gel which operate in such devices, and then it is important to see that there are boundary conditions. So obviously your material should have a certain minimum uptake of water, and what is best is if the loading water drops 0.3 kilogram of water per kilogram of oil. So the more the better. That is easy to understand. The boundary condition is that the relative water vapor pressure where the material absorbs should lie between 0.05 and 0.3. Should have an S shape, as you can see here from the green and violet or the orange curves. So if the material is too hydrophilic, like the blue curve here for zeolite, it's not good because it's outside this range, and also if the material is too hydrophobic, obviously it's not a material. And silica gel has a steady uptake, so a lot of the uptake of water in silica gel is then in too high relative water pressure. So that's why to look for new materials is a feasible issue, and MOFs come into play here, because MOFs, as I said earlier, are much more porous than zeolite, silica gel, and so on. And so MOFs, in principle, can take up much more water than the other porous material. And the record MOF in terms of water uptake, or one of them, is Bill 101, which I described earlier. And so Bill 101 can take up its own weight and even more in water. So over 1 gram of water you can absorb in 1 gram of MOF, or 1 kilogram of water and 1 kilogram of MOF. And at the same time, the MOF is highly water stable. So here it's shown that after 40 cycles you have no loss in water uptake and no loss in surface area. These values are within the error range. And more cycles and there will be no degradation. And that is not not necessarily to be expected, because MOFs are coordination compounds, so degradation or ligand replacement, because the water or ligand was in metal, can often occur. However, the drawback with Bill 101 is that it is too hydrophobic. So as you can easily see, the increase, the S shape here, falls into the region of 0.4 to 0.6, which is too high. It means too hydrophobic. Now, since we are chemists, we know how to increase hydrophilicity, and one way is, of course, to use other MOFs with slightly other ligands, close relative to Mil-101, but having a different ligand, is Mil-100. This is Mil-100 series. So Mil-100, for example, with iron or aluminum, has the water uptake region here in a more hydrophilic range between 0.15 and 0.45, and all uptake in terms of 0.75 gram per gram is quite good. Also, it is quite stable, so after cycles, little modulation, it would also be a possible more for this technology. Now, another way to increase hydrophilicity would be to introduce groups for hydrogen bonding, or amino groups, for example, hydroxyl groups. And this is shown here with two examples. So when you bring in an amino group, one group will you can increase hydrophilicity. So here now there's amino Mil-125, which is titanium morph structure shown here. You can see that the uptake falls into the region of 0.1 to 0.3 relative pressure, which is the region which I indicated to you before would be feasible. I should also point out that Dr. Vasile Lozan, who is in the audience, was collaborating with us here on the preparation and the investigation of this morph for this technology purpose. Now, aluminum morphs have been found to be very attractive also for this technology because the metal aluminum is very cheap. It's not considered very poisonous or not poisonous, and also aluminum morphs are very stable. And here we see the combination of Mil-160, combination has an isophthalate linker. Mil-160 has a furan carboxylate linker, and the issue with these morphs is very structure. So they are called structural, and this gives is a prerequisite that we can make a series of morphs where both linkers are combined. So when we come to mixed linker morphs, so by replacing one linker through the other, either starting with a pure isophthalate, Cau-10H, or with a pure carboxylate in Mil-160, we can make almost every ratio here. So from 96 to 4 down to 11 to 89, and these ratios here have been composed synthetically. That's why the numbers are a bit odd. But then we see that we can fine-tune now the S shape or the uptake region. So furan dicarboxylate is a very hydrophilic linker. Its uptake is here around 0.05. So, and isophthalate is less hydrophilic and not really hydrophobic yet. Its uptake is at 0.15. And depending on the ratio of these two linkers, we can make every step in between. Now you may wonder, is it really necessary to do that? Now in this absorption chilling technology, the temperatures at which you want to cool and the boundary conditions for the specific application require that you have to do a little bit more fine-tuning. Or it would be good to have this possibility. So this is of course only one aspect of implementing here a new material technology. A second aspect, which is even more important, is engineering type aspect. So coming back to this picture, showed cycles, you have big pipes drawn through this absorption material. Now these pipes are quite crucial, because in the infrared image you had seen earlier that the absorbent material gets hot during the water absorption, and also when you turn the process around, you have to supply heat of regeneration. So this is an important issue, because the heat which you generate here has to be dissipated quickly, has to be brought out of the system, because heating the absorbent material will counteract the absorption. So that means you have to have the morph in close contact to a heat exchange unit. So these pipes here, or the piping indicates to you that this is meant as a heat exchanger. So down here you see a realistic or real-world heat exchanger, and what we have to do now is to make a system or establish the shaping of morph that it comes with the contact with the heat exchanger. So there are different ways to do that. You can have a fixed bed system with pellets, fixed monomer, binder coating, and partial transformation. So we set out then to formulate the MOF into grains of pellets, which is here, 2 millimeter in diameter, and then we put these little pellets here into this heat exchanger. So here you see the filled heat exchanger, and we measured its capacity in terms of cooling power. And what we realized then is this cooling power of the MOF polymer composite is at the same size, 400 watts per kilogram of adsorbent, what you can reach with silica gel grains in these adsorption heat systems. So that means we are quite good also with our MOF formulation here as grains and pellets, but we can do even better, because the fixed bed system doesn't have really a good contact to the metal lamella. So when we use a binder coating, as indicated here, we get a better contact of the MOF system, because also the MOF particles are smaller here, and then we increase the contact, that means the heat transfer, and that leads to increased absorption rate and increased cooling power. So doing so, then we deposited the MOF onto the metal directly by different ways of either immediate formation, spray coating, or other means, and then the exchange of the bottom in the coating exchange gives a cooling power of 1900 watts at the vapor cycle, and the specific cooling power then amounts to 1394 watts per kilogram of adsorbent. So of course, when the MOF gets filled, the cooling performance drops, and then it would be time to turn the process around. So of course, it has to be also shown that the MOF layer is stable, and that's what was done here. So 10,000 cycles were measured of this K MOF here onto the aluminum foil, and then powder extrait diffraction was used to show that there was no change in MOF structure, so the MOF porosity was retained, there was no degradation. So this is also, that's why I said it's a good MOF for this application. So with that, I'm already at the end of my presentation. I have indicated to you or pointed out that MOFs can be used for an existing technology as a new material to improve the technology. That has to be overcome. One is so, for example, brought on two surfaces of to have intimate contact with the exchanger, of the membranes, or taking grains, or also monomer can be an issue. So all the top engineers, they tell you other things they want to have. So absorption kinetics, which plays a role in here, is an issue with thermal conductivity. The engineers have to be more thermally conductive, it would be better. Then they say, okay, if you use that process in an open mode, for example, humidification, to absorb water from air, there have to be anti-fouling properties. They ask you, can you make a large-scale synthesis of a MOF? Is it economical? How much will the MOF cost? Is the metal non-toxic? So, for example, the first MOF I brought was the chromium MOF. And if you talk to engineers and they hear chromium, they say, oh, it's terribly poisonous, it's carcinogenic. And if you set out then to explain that it's difficult to chromium, you say, okay, chromium is poisonous, unless chromium, give me another metal. So with that, then I point out to you that implementing chemical material into a new or existing technology has many issues. And the last thing is then to say thank you to my group and my co-workers who joined me in this work. So especially Dr. Stefan Henninger from the Fraunhofer Institution and our joint student, Dr. Felix Remias, who was very important in the beginning of this work, and students who are still with me, and also Dr. Vasil Lozan, who was collaborating here with us. And the money was given by these organizations down here. And again, I thank you for your kind attention, for listening, and for coming. Good question. Certainly, in this case, the polymer also included to make sure that the porosity of the rock over the surface area is largely retained. So we can now make, we can keep 80% or half of the initial rock porosity when we have it combined with the polymer. So we can 100% use a little bit, but at the most, we are now at the point that we can use only 10 to 20%. So if you do it correct, you retain the porosity. Of course, because it's a crucial and I cannot tell you that they are a good one.
Thank you for your talk. I just wonder how much growth would be needed to, let's say, to keep moving like this. Or in a small house.
Okay. Fully I cannot answer that because we are doing the cyclic fashion, and so it means the cooling, the speed of the rate of cooling is not so fast as the capacity. So how it's done is that usually these units then run continuously, for example, also overnight. So that you in a way pre-cool the rooms, and then during the daytime you can keep the cooling. That's why I also indicated that at present the technology is not so much used for the office or building coolings, but let's say for computer server units. So that's well known. These large computer server centers generate a lot of heat to be cooled, but they have a continuous operation. And it's there that, for example, this technology is really highly exciting.
My question is which kind of aluminium, because in general, the glues indicated, we use it for synthesis. It's hydroxide, oxide, or alpha, which kind?
No, we don't. Okay, we start aluminum salts, aluminum chloride, aluminum sulfate, or basic aluminum acetate. So it must be soluble salts. So you cannot start with certainly more cheap aluminum oxide, not the end.
Thank you. Thank you very much. Very nice talk. I have a few questions about synthesis. So when you use aluminum and chromium, yes, very silver, what's starting aluminum was acetate?
As I said, aluminum chloride, sulfate, or acetate, or basic aluminum acetate. Yeah.
And for chromium?
Chromium was, for example, chromium nitrate.
This is solid-thermal synthesis.
Solid-thermal, not as, I mean, okay, we use a solution process, but it's not necessarily in an autoclave. So the aluminum synthesis is done at elevated temperature, but not exceeding the boiling point of a solvent. So it's it's below the boiling point of a solvent.
So aluminum acetate was commercial.
Yeah, we only.
Yeah. Any trace of boron?
Of what?
Boron.
Boron?
Yes, because it's stabilized by boric acid. I'm telling you because I used this and I got in a structure with boron.
Okay, I'm sorry, I wasn't aware of that. That is a bit of a surprise that you say so that. Okay, we should. Okay, sorry, I'm not.
You never expect such things.
Okay, I will check on that. Thank you.
Thank you. And what is stability of aluminum molds versus chromium molds to hydrolysis?
Okay, chromium is certainly the best because that has to do with coordination chemistry principle, but aluminum is second or close second, but again, it was a poisonous nature, so chromium, you can forget it simply. It's difficult to implement in a, so aluminum would be really the metal of choice, most likely. I mean, maybe also zirconium, zirconium-4, but again, zirconium is more expensive, and also these zirconium-MOFs have stability problems. No, actually, the crystal structures I showed here are done by Rietveld refinement from powder X-ray diffraction, and there you could also use synchrotron powder X-ray diffraction. Yeah, these aluminum MOFs don't crystallize in very good crystals, so it's when a Rietveld refinement. Yeah.
Thank you very much.
Okay.
Next speaker is Professor Ion Gero, Academiei of Sciences Moldova Institute of Chemistry, and talking about time, reversal, symmetry in coordination chemistry.
Time reversal symmetry in coordinational chemistry. Time reversal symmetry is one of main discrete symmetry in the nature. The anti-unitary time reversal operator was introduced in quantum mechanics in 1922 by Nobel Prize winner Eugen Wigner. Up to date, there is a single consequence from time reversal symmetry for coordination chemistry, consisting in the supplementary degeneration of energy levels in coordination compounds with a ground state half-integer spin, or more generally, half-integer angular momentum taking into account spin-orbit interaction. Such coordination compounds are called Kramer systems because for them the Kramer's theorem takes place. According to this theorem, in a system with an odd number of electrons, there is a supplementary degeneration of energy levels due to Wigner's time reversal symmetry. I would like to show that there are three new consequences from time reversal symmetry for coordination compounds. One of them is inversion of spin levels of binuclear magnetic clusters in a coordination compounds under combined time reversal operator. Я покажу. Yes. The second consequence is the existence of structural distortions in Kramer's three homonuclear clusters due to presence of time reversal symmetry. Structural distortion due to time reversal symmetry. The third consequence is connected with the 6 ways of Wigner's time reversal symmetry violation and only 5 ways of Kramer's theorem violation in coordination compounds with Kramer's relation of energy levels. Подойдите сюда, пожалуйста. Сюда, может. Вот так, да?
Да.
Да. Окей.
Știi spate.
Yes. contains 7 type of time reverse symmetry. Time reverse symmetry operator spin 1, 2 of integer arbitrary spin, non-trivial factorization of the operator T, geometrical interpretation of time reversal transformation in Kramer's theorem, discrete and non-abelian group of symmetry containing time reversal operator for Kramer's systems. 2. On the violation of the Kramer's theorem, spin reverse inversion in unexchanged couplet pairs under combined time reversal, reference 2. Structural distortion in a trigonometric Kramer's cluster due to presence of time reversal reference 5. A virtual time reversal method is application of mass spectroscopy. 5.1 eval of dp/pH recorded during the natural flow of the time and its virtual reversal. 5.2 spectrum eval carbon nanotubes asymmetrical spectrum recorded during the natural flow of the time and its virtual reversal. Conclusion references. T is Wigner time reversal operator. There are also incomplete time reversal operators. In case of arbitrary spin, this is Wigner time reversal, U is a supermatrix, and T1, etc. are new time reversal operator, incomplete or partial time reversal transformation. Under such an operator, not all 3 components of angular momentum change the scene or are but only 1 or 2 for example. S6 projected, S6 projected charge the scene, S6 discharge, but S7 no charge, don't charge the scene. They represent the supermatrices U, V, W, it is unit matrix, sigma X, sigma Y, and sigma. The type of our matrices. For arbitrary spins is supermatrices. Wigner time reversal operator T and such way can be represented in form of product of 2 or 3 partial time reversal operators. This representation. Geometrical interpretation of the time reversal transformation and Kramer's theorem. It is the case for spin 1, 2. Half integer spin. This is a circle point in an arbitrary position. It is vector state in arbitrary time moment. And the time reversal this point passes to this position after an anti-rotation on a 90 degree around this axis passing through the center of the square. For such consequently transformation lead to reducing the system in the initial state. We have a square with 2 colored vertices. We can see, of course, the diagonal of this 2-dimensional cube orthogonal. It is a geometrical sense of Kramer's theorem. State and time reversal states are orthogonal vectors. Next case, this is half integer spin 3, 2. It is a 4-dimensional cube. And the same situation, it is initial state, The diagonal of this group are also orthogonal are constituency of Kramer's theorem. If now the spin is an integer value, have an integer value, for example, there is no Kramer's generation. It is initial state. It is after time reversal. Next, anti-rotation lead to returning system in the initial state, and there is no Kramer's degeneration. Discrete non-abelian group of symmetry containing time reversal operator. Such, we construct an group. This group is 16. S, the arbitrary momentum, containing all time reversal operators. Standard Wigner operators and 6 new operators in complex time reversal. The effect of Kramer's degeneration mathematically is expressed by a simple relation T squared equal to minus unit operators. It is condition for degeneration, Kramer's degeneration. If this C is not minus but plus, in this case we have a violation of this theorem. So, in case of new operators, we have 6 analogical relations, 1, 2, 3, 4, 6, but 5, but 16 relation is with minus C. In this case, the time reversal is violated by the Kramer's theorem is not violated. It's a single case. Attribution of T-symmetry, Wigner T-symmetry to Zx. In this case, the Kramer's theorem is not violated because it is not sufficient for removing the generality of energy level due to time reversal symmetry. Spin levels inversion in an exchange complex bars under combined time reversal operator reference to theorem. The inversion of a sign of the exchange interaction constant in an exchange complex pair is equivalent to the isomorphic substitution of one of the pair equivalent ions by an ion whose wave functions are time reversed with respect to wave functions of insubstituted ion. The proof of this theorem is contained in the book 2. So, the operation of combining time reversal is the following operation. T1, G, or T2, EG, where EG is an operator which changes the sign of constant directions. This combined transformation is equivalent to operation of isomorphic substitution of one of the exchange pair ion by time reversal ion. In particular, after such isomorphic substitution, the dimer copper 2 is transformed into dimer copper 2 vanadium 2, vanadium 2, experimental confirmation reference 3. Left, it is the spectrum of binuclear, homonuclear, CD9 configuration. Singlet state is grounded. That is the state. After such transformation, the inversion of flavor takes place. The ground state is triplet state. It is anti-ferromagnetic interactions, and the ground state, excited state is a singlet state. In 5, reference 5, it was shown our work that in the case of Kramer systems, so-called group of symmetry, there is not confined operators of rotation around three-order symmetry axis. As consequences, the equivalent magnetic atoms cannot occupy the vertices of an equilateral triangle and the structural distortion occurs because the extension of the 32 classical point group to 4-color point group of magnetic symmetry is fulfilled the structural distortion are due to presence of the time reversal symmetry. Experimental confirmation. This compound, coordination compound, has an magnetic copper 2 ions with exchange integral this value and ferromagnetic coupling. Using the isotropic exchange Hamiltonian, the ions copper 2 are arranged in a triangular phase zone with the difference copper-copper distances is presented these differences. Single crystal avea data at Q bands for spin total ground state 1, 2 lead to the non-coincidence of the parallel and the perpendicular as well as the difference copper-copper distances in a triangle agree with distortion of the trinuclear copper 2 clusters. So, existence of time reversal symmetry in this case leads to appearance of structural distortions, confirmed by experimental data. And now, a virtual time reversal method with application into a pair spectroscopy. Last year, we proposed a new method named virtual time reversal method. This method consisted in 3 steps. First step, the pair spectrum can be recorded in 2 ways. This figure. This is time axis, this is magnetic field axis. It is kind of increasing magnetic field. Somewhere resonance field, the FR line appears, FR spectrum. Second way is recording the spectrum of the same sample, but decreasing of magnetic field. At the same value of resonance field appears this spectrum. It is a mirror image of the spectrum reflected in this line. So we can do I and B. Next step is it is recorded by at increasing magnetic field, yes, that's A. Decreasing magnetic field, vector A with different phases, and the next third step is this is second spectrum, which is recorded. This plane is recorded. The spectrum together with plane is rotated by axis passing through center of the resonance line, orthogonal to magnetic field axis. Rotation by 119 degrees. In this case, the axis changes in and magnetic field is not decreasing but decreasing. Virtually change the sign of time and virtually change the sign of the derivative of magnetic field. After such a transformation, magnetic field. And the spectrum C, spectrum B, transformed by the sum of these two spectra of the same sample are the same, but the resonance fields are shifted because such a shift can be related to non-coincidence of oscillation of the magnetic field in the forward and reverse direction during recording the perspective cases A and B. It is a mechanical system, one direction, another direction rotation, and it's no equivalent. But after shift one spectrum with respect to another along the axis of magnetic field, please, we obtain the ideal coincidence of two spectra appear of the same sample, recorded by method at the increasing magnetic field, reported by and the flow of the time is natural flow, and recorded in the case of inverted direction of the time. The coincidence of two shafts of the spectra is confirmation that in this case there is no violation of time reversal symmetry. It is no result for a bar spectroscopy. If these two shafts are different, it is confirmation the violation of time reversal symmetry by experimental data. The same procedure we show for asymmetric line, a spectrum of spectra of single-level carbon nanotube. In this case, you can see a very asymmetric line. Case when recording the spectrum is at increased magnetic field. Next. Magnetic field. Next. Recording this transformation and we obtain this line. Comparison at natural flow of time and inverse flow of time. The same shift as in previous case, but after shifting of one line with one line with respect to another along the magnetic field, the ideal coincidence. In this case, also, the time symmetry is not violated. Global conclusions. First, there are 6 types of violation of time symmetry related to 6 incompleted time reversal operators. Second conclusion. The restoration of broken weakness time reversal symmetry can be realized by introduction of 6 types of metaparticles, analogy with antiparticles. 3. Because to each particle in the universe corresponds 6 metaparticles, plural. It means the existence of 6 meta-universes far away in space. See global conclusion. another non-global conclusion. 4. It was shown that along with weakness universal perspective, there are 6 new incomplete time universal perspective. It was observed that 5 bags of big universal it was found the existence of structural distortion in the form of magnetic clusters due to presence of time reversal symmetry. Time reversal symmetry lead to structural distortions. 9. It was proved that it is the most substitution in an exchange pair of ion by the time reversal one. The change of the scene of the change in the order of the spin levels emission. And then it was proposed a method of virtual time reversal with application of spectroscopy. In this case, we observe on the monitor the evolution of spectrum in if the time will be returned in opposite direction, experimentally. But such reversal of time is virtual reversal because about entropy for which reverse time this method allows to test presence or absence of the time reversal symmetry. References: Classical Beginner Publication 132. It is a book published in Premier. Next is book, Reversal Symmetry, 7 operator, 7 types of system. References 7 and 2. Thank you very much.
Question, please. Thank you. No questions. Next presentation will be from Professor Jean-Pascal Saquet, Coordination Chemistry Laboratory of CNS, Toulouse, France, and the title of the lecture is Pentagonal Featuring Journey from Magnetic Anisotropy to Molecular Magnets.
Okay, thank you. This one. Yes, okay.
this works. Okay, ladies and gentlemen, good morning. First, I would like to thank the organizing committee for the invitation. It's a great pleasure and an honor for me to contribute to these special days. So I would like this morning to tell you a little bit about the research we are doing in Toulouse in Coordination Chemistry Lab, and especially a project we have developed during the past years about the control of magnetic anisotropy and the construction of molecular magnets. So when you design a magnetic compound, you take into account mainly three parameters. These are the structural scaffold, the exchange interaction that will take place between your magnetic centers, and of course the magnetic anisotropy. So the structure is the chemical structure is very important because this will actually decide on the target you're going to make. If you target a magnet, you have to develop 3D structure, but if you are playing with molecular magnets, then a discrete structure will be necessary. The two other parameters here will contribute to the performance of your systems. So the interesting and the thing is that all these parameters can be controlled from a chemical point of view. I would like to illustrate these in the work done on these nanomagnets. So, what are nanomagnets? Nanomagnets are simply that magnetize, and the magnetization of the molecule will be somehow blocked, and relaxation of the magnetization will take place slowly. So when you design such kind of compounds, what you need is you need to introduce large magnetic anisotropy, and of course you have also to control the way you put these building blocks together. The building blocks we have investigated are pentagonal bipyramid metal complexes. So these kind of compounds are described here. So here's a few pictures we are using. So all these compounds are constructed using a pentadentate ligand that will occupy the equatorial position of your complex. In that way, the ligand will impose a general geometry that will be a pentagonal bipyramidal. So you can play with open ligands or with microcyclic ligands like those shown here. So these compounds have been described quite some time ago, but of course at that time nobody really looked into the magnetic properties. So when you take a compound made with nickel, for instance, so nickel in this geometry will be spin 1. So here you have the energy diagram of the orbitals. But this nickel will also display magnetic anisotropy that results from zero field splitting. So when you analyze these, the behaviors, what you find are axial D parameters that are negative and, let's say, between -10 and -20. So it's quite easy to assess this magnetic anisotropy simply by looking at the magnetization versus applied field at low temperature. So here you can see the plots for different temperature. You see that these plots do not superimpose, and this is a sign of magnetic anisotropy. And after you can analyze these data, these are the red lines here, and the analysis will yield the values I show here. I told you in the introduction that what we want to do is to use these compounds as building blocks and construct larger systems using cyanometalates. It was important to confirm that when you introduce a cyanometalate, the magnetic anisotropy will not be changed. And actually, it's not the case. So this is an example here. What we did is we took this nickel complex and we added a nickel cyanide. So this is diamagnetic, and when we analyze the magnetic behavior, we confirm that anisotropy remains roughly what it was in the starting complex. So the same is true for iron. So here, for one of the compounds, you can have negative D values again between -10 to -20. So this is how the electrons are organized in this iron complexes, in this geometry. What I show here is a result of some ab initio calculation, and I just want to point your attention to this blue arrow, and this blue arrow corresponds to the direction of the magnetic moment of your, I mean the axis of the energy in this compound. As you can see, the anisotropy is along the z-axis of the complexes or perpendicular to the equatorial plane, and the same applies for the nickel. So these iron complexes are quite interesting because they have a large spin state, SX2, and they show, let's say, quite large anisotropy. So for this compound, it's even possible to expect some slow relaxation of the magnetization. So, and this is indeed what we have observed. So for instance, for this complex, so this is just an isolated iron complex, we have slow magnetic relaxation. So this is something we can easily see by recording AC susceptibility measurements. And what I show here is the out of phase signal versus the frequency, and this difference relaxation of the magnetization going on. And from this data, we can extract relaxation times that are plotted here. So this is the relaxation time versus temperature, and you can see here we have a temperature-dependent relaxation that tells that for this compound we have indeed a single molecule magnet behavior, and these are the, let's say, the numbers we can extract. So this is the energy barrier that is related to the relaxation of the magnetization. So this is another example, just to tell you that it's, we observe it quite often. So this is a different complex, and again we have these relaxation time versus temperature, and again the energy barrier that is a little bit larger than what has been found for the previous compound. But this is not always the case. So very often we see nothing, or at best something that looks like this here. And what this here is telling is that you have a fast relaxation. So the reason for such kind of fast relaxation is mainly the intermolecular in the crystal lattice. So is this a problem? Actually, it's not. You can do some coordination chemistry, and for instance, what you can do is simply space your metal center, and this is achieved here. When you take this compound, you react it with, again, this nickel cyanide complex, you develop a chain, and now in the chain, the paramagnetic that are here in green are spaced by a diamagnetic linker. That means that now there is no interaction between these two. Magnetic anisotropy remains same, almost same as in a starting complex. And if you now look at the relaxation behavior of the what is a behavior that now tells you that you have a slow relaxation that is characteristic of the isolated metal center. This one, and this one. and again we can analyze this data and extract some energy barrier for the spin of the spin. Okay, so we have nice green units that show a large Ising type anisotropy, and they are without losing structure and anisotropy. And this is what you expect for a building block. So the step was to use these compounds to make some more complex species, and in this step there are some other points you are going to play with and to control. So one is to control the structure of your compound, but you can also, of course, control, and you will also control the interaction between the magnetic center. So one of the targets of this project here was to make a chain compound. When you look at this compound, you can imagine that if you substitute the optical position, it's an ideal building block to develop one-dimensional structure. So here's one example. So we take such a complex, this iron complex, it was reacted with an opium cyanometalate, and what was obtained is this compound that is a chain in which you have alternation between nobium, iron, and so on. So this chain strong nobium interactions, and of course this compound behaves as a single chain magnet. This is what you can see here. Now you're familiar with the AC signal, so you see this one corresponds to the out of phase signal, and you can see that there is a temperature dependence for these. There is a frequency dependence for this behavior, and it is magnet. You expect also the opening of hysteresis loop, and indeed this is found for this compound. It's shown here. So here what I show is magnetization versus light field. So here is 0, increased field and decreased field, and you see the opening of hysteresis that actually takes place at quite low temperature, because here we see opening of the hysteresis only below 2K. I would like to talk about that is, so what I plot here, and these dotted red arrows here materialize the direction of the anisotropy of these of each of the iron center. And what you can see is that actually these axons are already of space, and if you do a projection, let's say on the axis direction, you can easily understand that the macroscopic anisotropy of such a chain will not be very large, and this may explain why the energy barrier we get for this compound is not so large. It was a little bit deceptive to us when we analyzed these data. So what it means is, if you want to improve the behavior of electrons, you have also to take care about the alignment of the local anisotropy. Here again, you can quite easily do it in chemistry. So what we did is we now use cyanometalate as assembling unit. It's this chromium bis-cyanide compound. And here you have the two cyanides that are in transposition of this chromium complex. So when you react to species, you indeed develop a chain, and this is a view of a fragment of the chain, and you can see again in green the iron center reached by the chromium, and this looks quite linear. Here in this movie, what you should see is blue arrows that are here here. It's not very clear in this picture, but the blue arrow, so this is the anisotropy that has been calculated by ab initio calculation performed on this chain. And actually what this calculation shows is that the easy axis of the anisotropy are tilted by a maximum of 10 degrees. So for this compound, just a few plots of magnetic behavior. So it's a chain, and this is the variation of height or mu effective versus temperature. And as expected for chain compound, you have a rise at a low temperature. We can analyze that to extract the exchange interaction between the iron and the chromium. For an anisotropic chain, what to expect also is an exponential growth of the magnetic moment at low temperature in zero field, and this is shown here in this plot. Here, what I show is chi prime t versus 1 over t, and this linear part here is actually corresponds actually to the exponential increase. So to say that from such kind of data, you can also extract some correlation energy that occurs in this compound. So of course, this compound behaves as a single chain magnet. So this is a chi-second versus a frequency for different temperature. When you analyze this data, again, you can extract the relaxation time versus temperature. So I don't want to enter into the details. If you have here two lines, it's because we see the difference between the behavior of infinite chains and finite chains. So this means chains for which there is somehow a mistake that makes that there is no infinite growth of the magnetization. So we can analyze these things, and what we get now is an energy barrier that is above 100 K. It starts to be an interesting value for this kind of chain systems. And of course, we see opening of hysteresis loop that now takes place at a higher temperature. So in blue, this is at 2K, but you can see that even at higher temperature, here 3 and 5, there is still like hysteresis. Very recently, we applied this approach also to nickel compound. So I don't want to develop because I don't have time for that. So here we choose nickel because we targeted larger exchange interaction between these two centers. Just here, a view of the structure. Again, we have a chain, and now the nickel centers are almost perfectly aligned because there is an angle of just 4 degrees between the mean planes of these centers. So this compound also behaves as a ferromagnetic single chain magnet, and this is the energy barrier we have obtained for this compound. So time to sum up. So what I wanted to show you today is that pentagonal bipyramid complexes can be a very interesting building block that you can use with a very control of the magnetic anisotropy you have for these compounds in starting material, but this anisotropy is also kept in the let's say in the polynuclear compounds you're going to construct. So iron 2 is already just a single molecule, is already a single molecule magnet. And an important point I have stressed here is that when you design this kind of compounds, so exchange interaction, anisotropy of the building unit is important, but there is a further very important point, that is the anisotropy of your local centers must be aligned to reach the highest possible anisotropy and the augmented performances for your molecular magnets. Before finishing, I would like to thank the people that have been involved in this project. So these are the chemists that have been working with me in Toulouse. These are some collaboration with physicists and theoreticians that have contributed to this work. I would like again wish a very happy birthday to your institute and all the best for the next 60 years. And finally, I would like to thank you for your kind attention. Thank you.
Thank you for your journey to Moldova, to give this very interesting talk. So, questions, please.
Yes. In what respect does the magnetic anisotropy depend on the electronic configuration of metals? Or in other words, would manganese or cobalt would also be it?
So, the magnetic anisotropy is very much related to geometry and electronic configuration. So here the compound, let's say the metals we are playing with are iron and nickel, because we know that for these compounds, also the D6 and D8, high-speed configuration, we will reach an actual anisotropy. With cobalt, you have also a strong anisotropy, but for cobalt-2, the anisotropy will be a planar anisotropy. So this means it's not an anisotropy that wants to align along an axis, but that stays in a plane. You can also do things like that, but it's a different story. I mean, it's more difficult because at the end, what we want is in the macroscopic system, we want to have an actual anisotropy. Yeah. And with manganese too, there is no anisotropy at all, because you have one electron in each orbital.
Questions?
The second one is, and maybe you said it, but when you have chromium, because chromium also has electrons,
yes.
you have a magnetic coupling then?
Of course. We choose chromium because we know that chromium with nickel, we have a ferromagnetic interaction, and this interaction might be large. So in this compound here, that I showed, we have a ferromagnetic interaction around 12 wave numbers. So it's not very large, but let's say it's not so bad.
Thank you.
Thank you very much.
This was in this session, and we have a coffee break until 11:30.
Sergei Michalowski from Leiden, the presentation will be on structured fossil materials for nuclear radiation from mercury and arsenic. So, looking forward to the presentation. Good morning, everyone. So, first of all, I would introduce our quite international team, and I can say that probably during my lifespan I have spent some time in each of these institutions, but if I put all five it will look a bit awkward, so I decided I will just leave the latest two. This is the presentation in which I'm going to talk about our approach to developing new materials, new adsorbents for highly selective removal of mercury and arsenic from water. First of all, why arsenic, why mercury? Well, according to the definition of the World Health Organization, 4 out of 10 most dangerous elements for human health are heavy metals, and of course arsenic and mercury are among them. And this is the table which gives you the summary of the maximum allowed concentration of mercury, arsenic, and water in air, and brief summary of what kind of health effects they may have to this contamination.
And I couldn't, of course, skip this very famous illustration from Alice's Lectures in Wonderland, because this is a Mad Hatter. And in the English language, being mad as a hatter is a sign of some peculiar behavior of hatters. And that behavior is assigned to the fact that the hatters, when they made their felt hats, used their brain. That's why their behavior became brain. Not only according to the organization, these elements are very dangerous. In the States, they revised the substance realists, Interestingly enough, it be back to the slide. I do it differently. If we go to this slide, somehow that's the one. Yeah. You see that in principle the requirements for the medical are more strict than for arts. Nevertheless, arts is more dangerous, number one. Because arts is a much more abundant element in the aircraft, and because the potential of plastic is higher, because of the sheer amount of plastic available for consumption, air, and food. The latest established very strict guidelines for student work, and you can see that actually mercury is much more than cadmium, which is considered to be completely alien element to anything living. That resulted in the design of the Minamata Convention, which is an international agreement, which aims at complete phase out of production, because this is the only way to make sure that we may of our exposure. It's just to stop using. The way I did my yesterday publish, I looked at the attitude in different countries to the Minamata Convention. I looked on the countries which are present at this conference. You can for yourself where your country is, and there's also the several consigned ratified, which is the complete accession to this Minamata Convention. Some countries signed but not ratified, and some countries didn't sign. Unfortunately, this is the two countries signing but anyway, this is the state of the Minamata Convention at the moment. Anyway, it is in action, because once it has been ratified by 50 countries, it is in action. Now it has been ratified by 150 Now, what is the problem with it? Here on the one hand, when you look at the map, you can see that those highest emitters of mercury are China, India, some European countries, and some African countries, and they mine gold using mercury. But the problem appears to be much more scary, if I can use this word. New data for 2015 suggests that, despite the fact that many countries, especially developed countries, try to reduce the use of mercury, the amount of atmospheric emissions of mercury is actually increasing. Moreover, only 30% of these emissions are due to new anthropogenic activities. 60% is the recycling of previous anthropogenic emissions, and 10% natural. So, although China now and India probably are the biggest emitters of mercury in the air, but the blame still remains with the developed countries like European countries and America. So that means this is because of the very specific environmental metabolism of mercury, it can reach anywhere. Recent reports in Nature found the mercury in Arctic ice. So it tells you the scale of the problem. Now, what are the new challenges? And that's why we decided to look into this problem and try to design a very selective absorbent for mercury. European Union in 2012 set up a new, much more, 100 times more stringent requirement for the level of mercury in surface water. So now, if in drinking water it still allows 1 ppb, but in the surface water 70 ppt, which is 100 times lower, and average of 50 ppt. So when in the new Environmental Quality Standards Directive suggests that once they revise the harm which can be caused by mercury, they made more strict regulations about the content of mercury in other media, like fish, for example. Now, the analysis of the existing commercially available removal technologies for mercury cannot reach this requirement. Simply, it can't, because it has always been aimed at trying to reach the level of 1 ppb, 2 ppb, half ppb, but not 100 times lower. So that's the reason why we need to look for new technologies, invent them, and obviously they have to satisfy certain requirements. Have to be very selective for mercury, otherwise you cannot take it out to such a low level. They have to be efficient for all types of mercury species. By the way, organic species of mercury are much more toxic than inorganic, but it has to remove all of them because the standards do not specify which type of mercury it is. And thus, of course, they have to be cost effective. And when we started looking at the possible solution, we decided that we'll try to exploit a very unique feature of mercury, forming amalgams with some metals. So some preliminary work which we did earlier produced these interesting results. So first of all, we played with the silica, because silica is a material which can be controlled in its surface area, porosity, and purity, whatever. And what we did first, you introduce silicon hydride groups, which are known to have ability to reduce some noble metals to the metallic state. This was the way how we produced silver nanoparticles on immobilized layers of silica. To prove that they are there, we use technical methods like iodine titration, but also we use which shows this case it is only this type of silicon hydride group, but some other silicon also show this type of silicon hydride groups. So it is there. And you can control the size of silver by changing ratios between the different components of this. What we discovered was interesting. Believe me, we had to check it many times to convince ourselves that it was we found that the reduction in the particle size silver raised the ratio of mercury per silver. This type of the plate for the line, and it is defying all the conventional knowledge about the stoichiometry of interactions between silver and mercury. So younger friends decided, young people like Porsche, so they called driver stoichiometry. I resisted, but there were more younger people than me. So what that means is that it's a small particle size of silver. In this case, we believe that the threshold is somewhere around 30 nanometers. Suddenly, the amount of mercury per silver goes up significantly. Okay, we don't know exactly what causes that. We just simply say this is a nanochemistry effect. How to explain it, we still are not sure about, but at the moment it doesn't matter. What matters is actually that we make an effective absorption to basically mercury. And just some experimental data we show that it is more or less like a granular type of isotope, plus kinetics. The mechanism, well, one would imagine maybe that's because they have similar redox potential, silver and mercury. It could be a redox reaction. To our big surprise, we found two things. First of all, the amount released into the solution after interaction with mercury was only traces. So most of mercury stays as nanoparticles. Moreover, these nanoparticles actually increase in size after interaction. So this is the size of nanoparticles before interaction with mercury. This is the size after. They grow up, which more understand. If silver remains there, and mercury just adds there as forming an amalgam. That fact that it is an amalgam is confirmed by the conversion from some sort of ordered crystal structure to more disordered, more amorphous structure, what amalgam is. So the answer to the question, what is the mechanism, is we have no idea. We looked at the literature, and most other groups which use a similar approach, they use additional reducing agent to facilitate reduction of mercury. We did not, and we found only one other group which did not use any other reducing agent. They refer to some sort of photochemical reaction, but we haven't studied it in depth because our main aim at this moment is which can remove mercury. Silica as such is a synthetic adsorbent, so it is reasonably expensive. We decided to try another material, which is called fly ash, which is a huge inductive waste, and it's not clear what to do this way, so we thought we will use it. It does have silica, which means that we can use the same approach as we used in the previous work. And the first step is to convert it into synthetic zeolite, and these are the steps how to do that. And then at some point, we introduce silver. In this case, we do use a reducing agent. So instead of immobilizing silicon hydride groups, which we could have done that, but we went for this alternative route. We used borohydride to reduce silver, and we produced silver nanoparticles immobilized on this synthetic zeolite. You can see from this slide different experimental data which prove first of all silver is there. These are these particles and the chemical composition of coal fly ash and etherite materials. Clearly show that this one, which is defined as silver containing, does have silver, whereas the other two don't. This is just a few images to show how the zeolite crystal grows on the fly ash particles, and on the right it is the absorption kinetics of mercury. You can see that actually it's fast for the absorbent containing silver nanoparticles, and it is very efficient. It keeps almost 100% removal of mercury from the solution. Whereas other materials which do not contain silver show, as expected, not so impressive performance. The particle size of silver has been analyzed using lithography, and you can see that roughly it is from 5 to 1 nanometers, average 10 nanometers, although I have to say that in this method of making silver particles, we cannot control it as well as in the previous part, because here it is not, the whole process is not so easy to control. But let's average 10 is a good result. To prove that mercury is absorbed by the silver side, these two images, I don't know whether you can see them. So in other words, mercury blue dots sit more or less in the same place where the silver dots, which are red in this case, which confirms that the main idea of removing mercury by this absorbent is its interaction with silver. Okay, if it absorbs mercury, it's fine, but what happens next? How tightly is it kept by the absorbent? So we did some leaching experiments, and we showed that even with very harsh treatments, the leaching of mercury after 12 days was very low, which means that actually this is definitely sufficient time to take this adsorbent away from the effluent and do something about that, and the mercury will not be dissolved into the solution. Now we move to arsenic. As I said earlier, that arsenic is a much more abundant element, and because of that, it does create larger scale environmental problems. Even in Europe, it has been estimated around 600,000 people, actually in Hungary, Romania, Croatia, Slovakia, I'm not sure about Moldova, I haven't seen information about Moldova, are exposed or were exposed at different times for various reasons to the high level of arsenic. That is because this area has a lot of arsenic in the rocks, which are situated in this area. And of course, there are some other places, Greece, Spain, which have particular sites with high level of arsenic, but they are kind of isolated and located. That's why they don't affect so many people. And what is common between arsenic and mercury? There are no effective treatments of chronic arsenic and mercury health effects, and there is no cure for chronic poisoning by mercury and arsenic. So the answer is, get rid of them if you can, and if you can't, get rid of them, because there is no other solution. So what we did here is, this is the latest work which I've been doing. Again, we analyzed different methods for removing arsenic from water. None of them actually can achieve a very high level of decontamination. So that's why we focused our attention on iron-based nanoparticles, because quite significant number of publications have shown that different iron-based nanoparticles can specifically, or if not specifically, but at least effectively bind different arsenic species. The most difficult of them, of course, is arsenic-3, because arsenic-3 quite often exists in the water as a neutral molecule. Neutral molecules are more difficult to remove than ionized. Also, arsenic is different from mercury in one significant aspect. If in organic mercury is many times more toxic than inorganic mercury, for arsenic it's the opposite. Organic arsenic is not so toxic as inorganic arsenic. And however, the problem using nanoparticles is this. First of all, health and environmental risks. Nobody knows exactly whether nanoparticles are safe or not. And because we don't know it, we say no, better test if they're safe or not before you can use them. Second, if you try to pack a column with nanoparticles, you imagine how high will be the flow resistance. And then, of course, it's difficult to remove them from the 3D effluent, although for iron, probably not such a big deal, because they can be magnetic and be removed by magnet. So what we did here, we constructed our three-dimensional adsorbent. So first we made, by Zoll gel process, the iron oxide gel. Then we embedded it into the cryogel, and I will explain on the next slides what it means. And eventually created this three-dimensional column, which is a scaffold made of cryogel, polymeric cryogel, and the particles, nanoparticles of iron oxide are embedded in its walls. I thought I had. Well, anyway, let's stick to this first. So the iron oxide gel itself looks like this. I mean, we had to grind it, of course, but in principle we get the particles of this size, roughly 5 nanometers. Yeah, you can see, but they agglomerate into larger particles like this. Then you can also see that they are really iron and oxygen, and they are together. So using XRT, we put this magnemite phase mostly. Now a bit more explanation about the cryogels. Cryogels were first reported in scientific literature by Professor Vladimir Luzinsky, Nesmeyanov Institute from Moscow in early 80s. Although whether he was the first to do it or not, I'm not sure, because I found the Japanese patent in which they describe synthesis of cryogels a few years earlier. But believe it or not, those cryogels were patented for making a bait for fish. So maybe it's not as relevant. So what you do first is, you mix the polymerizing system in which you put monomers, cross-linkers, initiators, all that. And then you, the system undergoes deep freezing, usually to the temperature -6, -20 Celsius, in our case to this temperature. And in this frozen system, the cryogel actually is formed. So ice works as a pore-forming substance. When you thaw it, you have a nice structure with large pores in between, and these pores are very well interconnected. We had experience of using these materials for other applications, usually biomedical, so we knew that it would be a good thing. So what we did here is, at this stage, we just add iron oxide gel particles, and they get embedded into the cryogel. So this is how this cryogel looks.
with a higher content of iron oxide and lower content of iron oxide. You can see large pores. I wouldn't call the pore diameter because I cannot imagine how you can define the diameter. So the pore size here usually is very large, like 220 to 100 micro, which is very good for the low flow resistance and very good for many technical applications. Transmission electron microscopy images show that these nanoparticles of iron oxide are embedded in the walls of the cryogel. The flow resistance looks very impressive. You can see until about flow rate. The flow rate through the column actually follows the flow rate through the empty column, through the column of cryogel. So it shows practically very low, practically zero flow resistance. Then something happens at higher flow rate, probably some internal pores collapse, and that creates some additional resistance. But again, you can increase the strength, mechanical strength of the cryogel by putting more iron oxide particles or by using different combinations of polymers. Here I will show just the way how it absorbs the Arctic. Again, it's classic Miller isotherm, and we compare different materials. And as expected, in principle, per weight, are most efficient weight, because obviously if they put in the cryogel, there is still some hindrance for the solution to come to the particles. However, the fact that nanoparticles can be evenly distributed in 3 dimensions, and there is no flow resistance, makes approach very potentially useful. To compare our results with other results, we look at other data, and you can see that in principle we achieve quite high efficiency in removing arsenic capacity compared to some materials. We do believe that we can improve it further, but also the important thing is that our materials are technologically capable of doing the job in the purification of water in the flow-through system. Kinetics is very fast, it's expected because we have very large pores. And importantly, as we go back to the issue of nanoparticles, I stay for early node. So we did some preliminary tests, and we looked at the cell viability and cell lysis for the leaches which come out of the cryogels, and we show that they do not differ from the control, actually probably better than, some of them better than control, so they are safe at least in these experiments. Conclusions. 3D, three-dimensional structured materials with embedded nanoparticle can and have been designed for highly selective and effective absorption of mercury and arsenic species. Cryogel-based constructs have shown low flow resistance, so like technological, and the mechanical strength can be further improved. We do need to understand the mechanism better than we do now, because that may help us to further optimize and improve the performance of the materials. And that's why also scientifically it's quite interesting what happens there, because it again may lead to some scientific discoveries. The work was funded mostly by the European programs, Program 7 and Horizon 2020. A long list of other people whom I didn't put as co-authors, but who contributed to this work in one or another way. And specific multimedia speciali, if my pronunciation is correct, to organize the committee, which Lupan here. And I'm not sure I will pronounce that. Thank you for your attention.
Yeah, thank you for this report. Questions, please? Well, maybe I can start the question. Is there a possibility or if you consider to regenerate your sorbent materials?
That's a good question. In principle, we are still not sure whether it is worth regenerating them. Because, for example, although silver looks like it is an expensive material, but if you think about the concentration of mercury we're dealing with, we calculated that we need something like 10 grams of silver to decontaminate something like 10 million liters of water. Well, I mean, of course, if you talk about heavily polluted, that will be a different story. So in principle, it is possible, and literature shows that you can regenerate silver from its amalgams. Whether it will be worth it or not, we need to calculate not so much chemically, but economically. About arsenic, I'm not sure it is worth regeneration simply because iron oxide is, even in a nanoparticle size, is relatively cheap. So probably it will be better simply to try to reduce it in volume and store somewhere. Because, let's put this, even if you regenerate it, what it means is you regenerate the sorbent, but you still have to deal with the mercury and arsenic. So we come back to the headache called environmental metabolism of arsenic and mercury. So at the moment, the answer is yes, it is possible to regenerate. Whether it is worth it still has to be analyzed.
Just wonder if the silver nanoparticles can really be used in a normal situation, in a normal purification process, because silver is quite unstable.
Is what?
Unstable.
Unstable.
It's very easy. Or you may react with other species, or whatever.
As I said, it's true, because obviously there are some other potential competitors for silver nanoparticles. I don't think you can oxidize it that easily. You do need to have a reasonably strong oxidizing environment, or you need to keep it exposed to this oxidizing environment for some time, not just in a minute or so. So in that sense, I wouldn't be too much worried about whether silver oxidizes or not, but whether it will react with other substances is a different story. However, if we consider silver might react with chloride, because it has good affinity with chloride, and that is probably the main competitor with mercury. However, I'm now speculating. I do not have this. We did some experiments about that, but we are still not sure. We didn't complete them. However, the good thing that mercury also has good affinity with chloride. So in that sense, and we do have some evidence for that, when we dealt with the zeolite with silver nanoparticles, we actually looked at the absorption of mercury from mercury chloride solutions. And we found that actually there is definitely formation of silver chloride, and there is definitely attachment of mercury to silver chloride, as well as forming an amalgam with silver. So maybe we are lucky in this case that silver and mercury will be like l'amour de trois with chloride, and that probably will solve the problem. But your question, let's put this, it's not maybe necessarily $10 million question, but $1 million definitely.
So you were showing that the stoichiometry of this silver and mercury, when you are decreasing the size of the silver, you have an increase. And as far as I remember, it was 1.2, the last one.
Yeah.
So is there any stoichiometry for this amalgam, so that you reach this stoichiometry?
Well, that's an interesting thing, because the stoichiometry, when you look at the silver-mercury phase diagram, it definitely shows formation of some compounds in which actually the ratio of mercury to silver is lower. So it is really something about that, something new. So, but as I say, at that moment we were puzzled, but we decided not to stop on that because God knows how long it will take to understand why. We just moved on to the practical application.
At the moment, I don't see any further questions. Please join me in the speaker again.
Thank you. I'm happy to talk to you after.
We don't have mercury anymore.
But Romania does. No, arsenic. We talk about arsenic.
Yeah, so our next presentation will be given by Professor Joachim Silvestro from the University of Academiei, and the title of the presentation will be High Performance of Gas Pipelines, process for short piece.
Okay.
So first of all, I would like to thank the organizing committee for the invitation to join this conference. We are here because I belong to the University of Alicante in Spain, and we are participating with the Institute of Chemistry in a European project, together with some colleagues that are here in the audience from Ukraine, Slovakia, and a few other countries. So that's the reason why we are here today, and I would like to share with you part of the research that we are doing at the university in Spain, dealing with synthesis of carbon materials and application of these carbon materials for gas storage. So as you all know, at the moment, if we are dealing with natural gas storage or with methane storage, we have two possibilities. One is to work at really low temperature and low pressure, so we can have liquefied natural gas. We can use these big boats to transfer liquefied natural gas from, for instance, Saudi Arabia to Europe. Or if we are thinking about automotive industry, we have the option to work with compressed natural gas. So we can use that. We are working at room temperature, and then we can have a huge, an important storage capacity, in this case, to run the car with natural gas. However, in both cases, those are highly demanding conditions, because either we are working with pressure or we are working with high pressure. And of course, if we are thinking about a car working with 250 bars or even above, this can be really risky in case that you have an accident. So one of the things that we are trying to do is to develop, as I say, carbon materials where we can define the porosity of the system and we can have a maximum storage capacity, in this case for natural gas, so that we can be working at a lower pressure. You see that instead of working at 20 or 25 megapascals, we can be working at 35 megapascals, and we can be working also at room temperature. And the idea is to be more or less the same storage capacity that you have at the moment in the compressed natural gas. So that means that our main goal is to design carbon systems where we can work, we can play with the nano-confinement effects. And final objective is to reach these 263 volumes of methane per volume of absorbent, which is the actual DOE target that we have for our materials. So you all know, or you're familiar with the activated carbon. So the good thing about activated carbon is that we can play with the synthesis conditions, and we can design the porosity of the system. So at the end, also we can play with the surface chemistry, and we have an unparalleled flexibility compared, for instance, to zeolites or to metal organic chemicals, which are like the new materials that we have at the moment in the pool. So you know that when we have a carbon material and we have porosity, what we have is an increased absorption potential. So we can trap the methane molecules and we can have an increased packing density compared to the natural system without the absorption. The problem is that if we take a look to the literature, this is a paper that we published in 2015, and you see that our best carbon, which is this one here, this is made from activated carbon, from petroleum pitch, and you see that we are able to reach these 263 volumes per volume, but we have to be working at 10 megapascals. And as I was showing before, the main goal is to make materials that are able to work in this pressure range, so between 3.5 maximum 4 megapascals. So you see that the carbon materials, they are far from the value. As I was mentioning, we have also other options. We have zeolites, but the zeolites, they are separate from this value. And nowadays we have also the metal materials composed by organic compounds like metal clusters and organic molecules. These materials, they are really good, and this is one example. This is a MOF, which is HCUS. This is copper PDC. You see that this material is extremely excellent. You see that we break the system and we go from here to the brown color here. So this is an advantage. Carbon is really strong, so the mechanical properties of the carbon are really good, and we can make monoliths without breaking the structure of the material. So now the question is, how can we improve this storage capacity for methane? So we need to find an option to double at least the amount of methane absorbed. This is just the example that I was showing. If we take moths, and this is a study from the guys in Chicago, in Northwestern University. If you take the moth and you apply pressure by your hand, you can break the system very easily. So this is an advantage that we have, as I mentioned before, in the carbon. The carbon have higher mechanical properties. The question is, how can we improve the absorption capacity of carbon? So the best we can do is just to check or just to see what happens in nature. If we go, for instance, to Siberia, or we go to the coastline, we will find that nature is able to store a large amount of methane in the form of methane clatrate. So that means that in nature we have a lot of water molecules that they are organized in a shell, and inside we have individual methane molecules. So that means that if we mix water with methane and we are able to make this three-dimensional structure, maybe we are able to improve the methane absorption capacity. So you see, this is the structure of the clatrate. So you have water molecules. They make like a shell, and inside of the shell you have one molecule of methane. And we know a priori that the capacity of this methane hydrate is really high. So the question is, can we try to do the same crystals in the cavities of our carbon material? So what we did is, that was done in 2015, we took one of our best activated carbons, where we have microporosity and we have also meso and macro, so we have a huge variety of porosity. And what we did is the following. We took the cavities and we filled them with water, and then we put the system in the absorption equipment to see how much methane we can absorb. So this is the dry material, so whenever the cavity is empty, we can absorb more or less 24% of methane. If now we fill the cavity with an increased amount of water, at the beginning you see that the isotherm is mainly flat, so that means that the cavities are blocked. But in a certain moment when we are above 50, 60 bars, you see that something is happening. So this is the methane capacity, and the system is somehow is not reversible in the absorption and the desorption. We put more water in the cavities and you see that something is happening. This is 1.8 and this is 4.1. So you see that when we have 4.1 grams of water per gram of carbon, we are able to multiply by 2.5 the methane absorption capacity. And whatever is happening there is not reversible. So there is a delay in between the absorption and the desorption branch. So now the question is, okay, what happens in these conditions when I have water in the cavities and I put the system in contact with methane? I just forgot to mention that all these experiments, they are performed at 2 degrees Celsius. So we are really close to the temperature of the ice formation. So the first thing that we were observing is that the kinetics of this process, they are really fast. So whatever is happening here in the isotherm, usually it takes more or less like 1 hour, 1 hour and a half. So that means that something is happening in the cavities of the carbon, and more or less in 1 hour and a half, we are able to finish with this process. We were calculating how much water is inside the cavities and how much methane we are absorbing. And you see that when we do these calculations, so we know already how much water we fill in the system, and we know from the isotherm how much methane the system is absorbing. And when we do these calculations, you see that more or less we have 1 molecule of methane, and we are always jumping in between 4 and 6 molecules of water. If now we go to the seaside and we check the natural cut rate, we know that the stoichiometry is 1 molecule of methane, 575 molecules of water. So this is an indication that we must be quite close to make these crystals inside the cavities of the carbon. The next thing, or the next step that we did is we went to the neutron facilities, and we wanted to see if we have methane isolated in the cavities. Because when you fill the carbon with methane, the rotation of the methane molecules is overlapping with another one, and then you don't have any signal. But when the methane molecules they are isolated, you can see a very beautiful peak of the rotation of the methane. So this is what we did. We had the carbon with methane, and you see nothing. You see that here mainly flat. But when we do methane with water, so we make the methane hydrate, you have this beautiful peak here. And this is an indication that the methane molecules, they are separated one from the other. So that means that This is again an indication that most probably we have cavities, and they are dependent one to another. And then the last experiment that we did is we went to the synchrotron, we put water in the system, so you don't see anything, then we made ice, we went down with temperature, so you see the hexagonal ice here. And then what we did is we filled the chamber with ice plus methane at high pressure, and you see that we were able to make these peaks here. So it was a change in the X-ray diffraction pattern. And those peaks here are a confirmation that we have methane hydrate crystals inside the carbon. So this is nice because that shows that we can more or less reproduce what we have in nature, and we can take the carbon cavity, we can put water inside, we can make ice, and then we can fill the cavities with methane molecules. Then the second, this is missing. So the second thing that we were doing is, we know that we can make methane hydrates inside the cavities of the carbon, and here there are two figures that they are missing, but the idea was to try to change the molecule that is inside of the clatrate. The idea is, can we take this methane out and put CO2 in the place of the methane? And that was more or less the idea of the second part of the project. We wanted to exchange methane by CO2 so that now we can go to nature and we can just fill this natural hydrate with CO2 and take the methane with us. No? And this is an idea that we were discussing one with a Japanese colleague. If we can make these artificial platforms at the seaside, and we can take the methane and fill it with CO2, we can use this as a combustion, as a fuel, and we can use these platforms to put the CO2 until we have an option for the CO2. And this is what we were doing at the synchrotron. The idea was to make the methane hydrate, and then in a certain moment try to exchange methane by CO2. So at the beginning what we did is we checked the stability of the methane hydrate, because what we have to do is we have to put water, we have to put high pressure methane, we made the crystals, and then we have to pump the system to put the CO2. That's why we had to cool down to minus 120. So we were going to minus 120 Celsius, we were doing vacuum, and then we were checking which is the stability of the methane hydrate. So you see that when we reach minus 60, all the methane is out of the system, and then you make ice. So we know that more or less minus 60 is our limit in terms of temperature. We also check reversibility. This is the methane hydrate. Then we do pumping, and then we have what we call minus 60. We have ice. We put again methane. So we have a reversibility. We can fill the cavities with methane. We can empty them, and we can go to ice. So that means that the molecules are highly mobile, and you can work with the system by this. And then the last experiment was, okay, now we do pumping. We fill the chamber with CO2, and let's see if we can replace methane by CO2. So again, what we did is we put at the beginning methane. We were growing the methane hydrate. Then we were pumping the system, introducing CO2, and then increasing the temperature to see what happens. So you see that at the beginning we have methane hydrate. We are increasing the temperature, and when we reach minus 6, we found that we are going for ice. So that means that Celsius to go inside, the methane is leaving the cavity, and you get a structure of three-dimensional ice. And then what we were doing is we were increasing the pressure of the CO2 from 1 to 1.5, and you see that in this case, we were able to make CO2 hydrate. So that means that at the beginning we have methane in the cavity. When we are warming the system, in a certain moment methane is out. So you make ice, and then when you increase the pressure of CO2, CO2 is able to go inside. So this is a confirmation that we can play with the nature of the molecule that is entrapped in this habitat. And with this, I would like to finish my presentation by just showing the conclusion. So the idea is that we can play with the synthesis of the carbon material. We can make an excellent carbon, but even when we have really good porosity, I show you that we have a lot of difficulties to reach the DOE target of the Department of Energy of the United States. So one option to improve this absorption capacity is to play with this clatrate or this hydrated structure. So we can fill our cavities with water, we can put methane, and we can grow these crystals, and we can improve quite a lot the absorption capacity of our carbon materials. Just to finish, I have to say that we were trying also with zeolites and with mobs. And the problem is that if your material has a lot of hydrophilicity, so if the water is interacting with the walls, you cannot make the hydrate. So the good thing about carbon is that carbon is quite hydrophobic. So that means that the water, instead of interacting with the walls, prefers to interact with the methane and to make this crystal. So if you are working with carbon materials, you have a perfect system to grow these confined crystals in your cavities. And just to finish, first of all, I would like to thank Professor Rodriguez Reynoso. He was the one that initiated all this research. So he is now retired, but he is every day coming to the university to discuss with us all the results. So he was one of the first that initiated the research in carbon materials in Spain 35 years ago. And of course, all my colleagues, the Nano Magnets project, where the Institute of Chemistry here is also participating, and of course, all of you for your attention. If you start with the ice phase and then you put CO2, you can make a CO2 hydrate at a much lower pressure than the methane hydrate. So that's why we were thinking, okay, if you start with the methane hydrate, which is the one that you have at the moment in the seaside, the idea was, can we replace methane by CO2, taking advantage of this higher stability of the CO2 hydrate? The point is that in the experiment that we were doing at the synchrotron, we had a limitation of the condensation of CO2. So I need to cool down the system to -100 so that I can pump the system, remove the methane, and then fill it with CO2. But when I do the filling with CO2, I have a limit of pressure because I don't want condensation. And that's why we were limited by this pressure. And going up in temperature is when we just saw that we were going to ice. And the only way to fill the cavities with CO2 is to increase slightly the pressure of CO2.
What is the aim?
The idea is to see that we can do the in-situ replacement, because at the moment, I know that some countries, they are considering, there are two approaches at the moment. Some countries, they are already taking the methane hydrates from the seaside, like for instance Japan. But I know that, for instance, in Canada, they are trying to do this in-situ replacement so that you can fill, without breaking the stability of them, you fill the CO2 while you take the methane from them. And the idea is to make that in the milder conditions so that you don't have any earthquake, you don't break the stability.
European politicians recently suggested we need to sign a special document which has the meeting in our gas. We will consider combining your approaches to the see the thing is, it's like the connect. Politicians decide it, and it's your problem how to do it. So I think this is again our problem how to do. So what do you think about kind of 20-year perspective in terms of the research into these kind of applications?
I mean, we are changing to hydrogen. You know that at the moment, we are thinking about the storage of hydrogen in a car. We are not talking about 20 megapascals, we are talking about 70 megapascals. So we can also play with this hydrate, and we can make hydrogen hydrate at a much lower pressure. And it's even nicer because in each cavity, now you have the option to put even up to 4 molecules of hydrogen. Because in this hydrate, you have big cavities and small ones. In the big ones, you can put up to 4 molecules of hydrogen. So this can be also applied for hydrogen in a few years from now, so that you can store the same amount of hydrogen but at a lower pressure compared to the actual. But you have to convince them that they have to put an absorbent inside the system, put water there, and I will see.
I also have a question. When you remove the methane, when it's in hydrogen, whatever you put in, what happens to the water? Does it not come out?
No, because we are usually working at 2 degrees Celsius. So it's true that if you are thinking about reversibility of the system, we have to be below 0, because if not, we are losing some water we are losing also reversibility. Yeah, you're right. That depends on the temperature that we are considering for the system. If we are above, if we are at 2 degrees, for sure that with time you are losing part of the water. If you are below, you have more probabilities to keep it there.
I agree, I understand that you have a fundamental scientific question or study, but you may know the fact that PS, for example, developed a MOF put in tank of a commercial national vehicle. So they had everything was done. It would be commercially put in the market, but nobody wanted to pay the money which it would cost to fit the tank with the MOF to get, let's say, 20% for the driving range. So then, since
I was telling some of the guys here that we are also now working in a paper where we put them off. You put it only 3 hours in a potential methane gas contaminated with H2S, with some acidic molecules, and in 3 hours you are able to damage the moth completely. So you need clean methane, you need the high cost, you have to pay for it, and be careful with the stability if you have also water there. So the end carbon is much better than that.
Okay, please have a question. If not, please join me thanking the speaker again.
And the first author is our invited guest, Professor Stefano Ubaldini, the key presentation, exploitation of secondary raw materials, application of innovative processes for valorization of mining waste.
Thank you, Mr. Chairman. Good morning, ladies and gentlemen. It is my pleasure and honor to present a plenary lecture in the framework of this very important anniversary from the foundation of the Institute of Chemistry. Thank you very much to all the organizing committee for invitation. Thank you to Professor Professor Igor Pova. Thank you very much. I go to start by my presentation prepared in cooperation with between my institute and the Institute of Chemistry in the framework of international bilateral cooperation with the financial support of CNR and Moldovan Academy of Science. Main objective of our common studies are mainly the valorization of secondary raw materials, such as mining and industrial wastes from electrical and electronic equipment, wastes from abandoned mines, by transforming wastes in resources and heavy toxic metals in useful metals. Applying sustainable, innovative technologies such as biohydrometallurgy, electrochemistry, integrated chemical biological processes. These technologies permit the following approach: versus green economy, blue economy, reduced and circular economy, with the aim to achieve the main products such as precious metals, valuable metals, critical raw materials. Examples are residues from industrial processes, dating from mining operations, and also scrap of metals from the collection of life products. We waste from electronic equipment. We are very pressing for the recycling of metal components, such as precious metals. However, they don't require extraction and treatment being available after collection in urban centers, with significant economic and environmental benefits. We are not only rich in metals, but are rich in metals carried critical. Your Commission has created a list of raw materials that define the critics, characterized by high economic importance and high risks associated with their supply. Critical raw materials are important for industrial activity, for the application of modern technologies and environment. We have the example of the main of the critical raw material in red, rare earths, antimonium, and indium, for example, are between the considered raw materials, critical raw materials. The main processes adopted for recovery of valuable metals, precious metals, critical raw materials are conventional and advanced. The main conventional are pyrometallurgy, physical separation, cyanidation for gold in particular, while the advanced processes are hydro-bio-electrometallurgical processes, suitable for refractory ores, extraction from low-grade resources, and the recovery of metals at a degree of purity, innovative integrated processes to achieve metals for reuse by the circular economy approach. Main advantages are low consumption of rare earths, the possibility to use low temperature, low energetic cost, selectivity of the processes, ease of the extraction, flexibility of the processes in particular. And now we have some example of the methods used in a large scale for raw materials that can be applied also to the processes for recovery of critical raw materials from the secondary raw materials. This example is the heap leaching, where the grid that mineral material is peeled into hills. And the next example, this is in the case of the use of microorganisms in this process, we have the heap bioleaching. This is an example of bacteria utilized in this process, the Acidiobacillus peroxidans. That these microorganisms can be used in the large scale in the heap bioleaching. In the United States, 25% of copper extracted is extracted by the application of this method, where there is the possibility of regulation of the this example as a percolation that permit the increasing of extraction kinetics and the recovery yields, recirculating the leaching solution. The next is this method is the leaching under stirring with the mechanical agitation system. In this case, this is the method by pressure. This method is used in the case of material of very high value. Now we have some example of the material that we have utilized during our experiments. We have collected examples from this area in Central Europe. This is a case of acid mine drainage. In this case, we have acid mine drainage near a mine in Peru. In this case, the acid managed water are rich in lead and zinc. In this case, we have the acid mine drainage from Slovakia. The mine is small, and this deposit is rich in copper and iron. This slide shows one example of our circuit of treatment applied in a specific case. This is the case of the alkaline battery. When at the end of the process is unrecovered zinc and manganese to start. This is an integrated process. The first step of the process involves the physical preparation, physical treatment, dissolving, smelting, grinding, washing, and after the start the hydrometallurgical steps with the leaching, precipitation, cementation, electrowinning, and the solution can be recirculated into the flow sheet, and this part is very important under the environmental aspect. This is an example of the flow chart of the physical hydrometallurgical processes when is present the first step of combination of physical treatment, chemical leaching, and is integrated by bioprecipitation. And you can also in this case we have the circuit closed when the liquid solution can be reused after integration of the process with final recovery of purified metals as final products. General main advantages of these technologies are innovative, economic, and environmental friendly. These processes will be integrated with physical treatments and the procedure followed by biometallurgical application. With the aim of a new solution producing useful metals, and the benefit for the environment is very important. Now I go to illustrate the case of study that consists in the application of innovative process for the realization of mining waste. Only an example of our treatment, but this treatment, the principle of this treatment can be applied also and final recovery by electrowinning. Yes, by electrowinning with recovery of metallic gold. The main results are very interesting because we have achieved a good kinetic of dissolution of gold with a recovery of about 75% gold working at room temperature. The recovery was selected towards the precious metals, and the conclusive point reached the social electrowinning was of about 70%, achieved metallic gold with a high degrees of purity. And it was possible to concentrate this gold. This is final laboratory that we have achieved after these preliminary experiments with the reach of social stripping, regeneration of the carbon that can be used during the adsorption phase, treatment of the wastes, and stripping. Also in this case we have a circuit of reuse of the reagent, and final recovery of metallic gold by electrowinning with a high degree of purity. For conclusions, the study to show the technical viability of the process. The dissolution rates of gold reached the final value of 75% working at the room temperature, and the complete recovery of the applying the integrated circuit was of 70%. Further activity, the results are very good, considering that it is an innovative process applied to a waste sample with a low gold content, and the optimization of parameters and operating condition with the subsequent scale-up in continuous application will permit to increase the process yields. Thank you very much for your kind attention. Thank you.
Thank you very much for your report. Some questions. Bold leaders in the please.
Thank you very much for your presentation. I have a question about interaction between activated carbon and gold. You refer to absorption only, but we had some experience with extracting noble metals from solution by activated carbon, and we found that there is a substantial number of functional groups of carbon which can reduce noble metals to the metallic state.
After extraction of the metal.
When you put carbon in contact with the solution,
yes,
noble metal, part of it is absorbed, but part of it is reduced and precipitates as metal.
With the stripping by specific alcohol, isopropylic, propylic, ethylic, with the ethylic alcohol we have achieved the best results. We can, with the high temperature in this case, with the alcohol to about 80 degrees of temperature, we extract all the gold. The levels of about 5% of carbon it's not possible reuse this carbon because during the process go in the washing water is not possible. Generally, it is possible recovery for after one step about 90% for carbon of carbon. After there is the washing of the carbon utilized with dilute acid, and after chemical regeneration at high temperature. After we can reuse in the successive step of the process for other tests in laboratory scale this carbon. But it's possible after 5-6 cycles we lose all the carbon, and it is not possible to reuse other time. Welcome.
More questions? Not more questions. Thank you very much for the presentation.
Thank you very much for your attention.
Thank you all the professors for today's very interesting presentation. All the people are very happy to have some good presentation from you. And now it's time for lunch. In the afternoon is a poster session, and in the other evening. In the evening at 6 o'clock, all the invited people come back.